Swayam Prabha. Digital India. Educated India.
Let's take a quick review of instruction execution. Okay. So before this, let's just get some terminology clear, right? Sometimes people use the words program, executable, process interchangeably, and it's better to use the right words. So a program is a set of instructions. Typically, we refer to the file which has these instructions in a human readable form. For example, if you write a C program or an assembly program and so on. Okay. When this program is compiled and an executable is generated, which is a file that contains machine level instructions which are in binary format. Okay. We cannot directly read the executable because they are not in ASCII format, cannot be readable, right? But these are in binary format and the instructions can be understood by the processor as it is. Okay. So this is still a file. A process is when we run an executable. This is a unit of execution on an operating system. It's basically a program which is in execution. So a process is kind of alive, okay? Whereas a program is a template for creating, sort of a template for creating a process, okay? So I hope this diagram will make it clear. So if you write like a program like simple.c, when you compile it using GCC, you get an executable, right? And when you run this, let's say you open two terminals and you run this two times, multiple times, not one after the other, but simultaneously if you run them, you're creating two processes, okay? So a quick question now. Suppose I have this C program and I compile it and I want to see what are the machine level instructions in this executable. I want to see what are the assembly level instructions corresponding to this simple program. Is there any way I can do it? Please write in the chat window if you are aware of it. Yeah. GCC O flag, the O flag in GCC stands for output name of the output file. So yeah, object dump is a utility. So the question was, how do you see? So one way is to not compile it completely to executable, convert the C first to an assembly level program, which is just a file which you can see and read. So instead of compiling all the way to an executable, you compile it first to an assembly level program and see that. Or if you already have an executable, you can view the disassembly using an object dump, right? So let's actually see that. Okay. Yeah, I hope you're able to see my screen. So here's a simple C program, right? There are three variables A, B, C, and then we add them. Okay. So we compile it using GCC. So this creates an executable called a.out. That's just the name. If I wanted to create a different executable, I could give the name of the output file. This is output my executable. Let's see. So this created my executable. Okay. Now if I run that file, let's say a.out, it prints the sum. The sum is 5, right? This is printed. So that's fine. So let's look at what happened to the code and how did it get converted. So this is my C code. So let's call object dump on. I use the flag D for showing the disassembly, for showing the assembly level programs. Disassembly. A.out. So it just prints it in the terminal. I want to put it in a file, so I'll just direct it to a file. Let's call it simple object dump. So I'm just copying these contents to a file, redirecting it to a file, and opening it. Okay, so here is the C program, and here is the disassembly of that program. Now, the first thing that you might notice is, although the program is very simple, this is huge. Okay, right. So how do we make sense of this? It's huge and there are many things here. So let's see if we can at least find something that is familiar. So we have this function called main, right? So let's try to find where is main in this. So by the way, I'm just opening it in a simple text editor. You can use any text editor like Notepad and so on. So I'm searching for a word main, and here it is. Okay, this is main. So this is main. So apparently the functions, this main function, whatever is here, is implemented as assembly level instructions here. Okay. If you look at this, can anybody tell me what is this? What is this value? 64A, and if you see 64A, 64B, 64E, and so on. Yeah, these are addresses. Excellent. They are all addresses. They are addresses. So apparently the main is starting at this address 64A. Okay, and if you see, this is in hexadecimal, so this is one hex digit, right? And how many are there? There are 16 of these hex digits. So that is 64-bit. So it is a 64-bit address, and that makes sense because I'm using a 64-bit processor, so Intel processor. Now, at the first location is the single byte. This is again in hex. So apparently this push instruction, push register base pointer, okay, is encoded as a single byte, 55 hex. So this is a single instruction of size 1 byte. Right. The next instruction is at the next byte address, 64A, then 64B. And the next instruction consists of 3 bytes, apparently. So the next instruction is move the stack pointer to the base pointer. Okay. And this instruction is encoded using 3 bytes. So this is 64B, 64C, 64D, and then next should be 64E, which is that's right. This is 64E. So you can see here, first of all, these are the addresses. The first column are addresses. The second column are the machine level instructions, the binary values. They're shown in hex format here. And you will also notice that some instructions are single byte. Some instructions are 3 bytes long. Some instructions are 4 bytes long. And here is a very long instruction consisting of many bytes. Why is this very long? Because look at this instruction. Right? We are moving some number into some register and so on. So that number is also here. Okay, let's try to make sense of what are these instructions. So these are the assembly level instructions, similar to the assembly programs that you might have written. Okay, it's basically, yeah. Is there any question? I heard some sound. Okay, so if any of you have a question, then feel free to unmute and ask. Okay, so is this address absolute address or relative address? So very good question. Okay, now this is what we will see in the later part of the lecture. But for now, assume that the last 4 bits at least is same. Okay, is the address that your processor will send out. Okay, this is a virtual address that processor will send out. The last few bits will be the same. Okay, so this is actually going to be at some location with some initial. This can be something different, but this last part is very likely going to be 64A. Okay, so this address is initial part of the address might change. Okay, so let's look at and let's see why that is. We'll see how virtual memory is implemented later on, but it's a very good question. But for now, the programmer's view is that this is the address. The programmer thinks that this is the address. Okay, let's assume it that way for now. but at least these bits are going to be the same, the last few bits. So these are the addresses, these are the instructions encoded into bytes, and these are the same instructions written in a human readable form. Okay, let's try to see if we can figure out where these are going. So the first is int a, b, and c. So somehow we are allocating space for three variables, int a, b, and c. Now let's look at here. Here, what's happening here is, if you have basically there is something called a stack pointer and a base pointer. Okay, so if this is a memory, and you must have heard of stack growing up and so on. So currently stack pointer was somewhere and the base pointer was somewhere. Okay, so now basically let's say here was the base pointer. The base pointer was pointing here and the stack pointer was pointing here somewhere, for example. Okay, so now let's see this instruction. Okay, so basically stack pointer, base pointer moves to stack pointer, so this now becomes the base pointer, and stack pointer is moved up. So stack pointer is, you subtract some value from the stack pointer. So this 10 hex is kind of 16, right, in decimal. So this is the stack pointer, and this is, it has moved ahead by 16 bytes. Okay, let me try clearly. So we have somehow this is the memory, and initially the base pointer register had some value, let's say some large value, let's say F000, and then stack pointer is 16 minus that, so 16 bytes are reserved. Okay, this is going to be the place where we put all our variables. Okay, so if this is base pointer, let's say it's at some address, at this memory address. If each of this is 32 bits, that is 4 bytes. And remember, this is the larger address. Okay, this is the larger address and this is the smaller address. So I'm just writing like 0, 1, 2, 3, and so on. Addresses are like this in memory. Then this is the address corresponding to the base pointer minus 4. This is base pointer minus 8. This is base pointer minus 12, and so on. Okay, so we are sort of using this space for creating our variables. Now what's happening here now? Look at this instruction. Move the value 2 into base pointer minus c. C is 12. So here I am moving the value 2, storing the value 2. Move the value 3 in base pointer minus 8. So the value 3 is put here in the stack. So basically here is the base, here is the base pointer. Okay, and this is sort of the area, the memory location that is being used by this function call. And I've placed the value 2 and 3 here. Now what is done? Copy the contents of this location into a register called edx. Copy this into some register. Copy this into some register. Then add them together. Okay, so add instruction edx and eax and store the result in base pointer minus 4. So whatever is the result, we'll store it in here. So 5 gets written here, right? And so on. So there is essentially some sort of a correspondence between this, and if you understand the architecture, then it's if you understand the instruction set, it's easy to figure this out. Otherwise, this might look very complex, but it's very interesting to go through this generated assembly. Okay, there is also a call instruction and so on. Okay, Now,
Excuse me, ma'am.
yeah.
Can you again explain after add what is happening? Like EDX and EAX are two registers.
So here is the instruction. EDX and EAX are added.
Yes, ma'am. And they are stored in EAX itself.
Yeah, so that's a feature of the x86 instruction set. The EAX is a default destination. Okay. If it's not written, the default destination is EAX, kind of like the accumulator. If you
But
have
it's
seen,
only in x86.
yeah, in Spark, you have to explicitly write the destination always. So if you say, you have to say three things, R1, R2, and store the result in R3. So you have to write all the three things. Okay, there is nothing called an accumulator. So it's just like a bunch of registers and you say what things you add, the source operands and the destination operands. In some other architectures, it assumes something called like an accumulator register. So if you don't say what is the destination, like say source 1, source 2, and destination, if you add them, if you don't specify what is the destination, then by default, it could be taken to be some accumulator register. So in Intel, it's like that, right? Also in 8085, if you have seen, there is a accumulator register, right? If you
Yes.
recall.
Yes.
So here, this is an Intel processor I have, and it's adding and storing it in EAX, and then that value in EAX is being stored in this memory location. So that's it's very interesting to look through this assembly. Okay. Now let's okay.
I have a small question.
Yeah.
How did how did it figure out that 16 bytes was enough for the stack? And what if I declare much more variables than 16 bytes can accommodate?
So let me show you the code. Okay. It's a good question. So if you are a compiler, right, and if I gave you this code to generate the assembly, if you are the compiler code, you can analyze this and figure out that first of all, these are already they are declared here in the scope, right? So these are on the stack. So variables like this, which in C, if you have done any, if you're familiar with how compilers work, so these variables will go on the stack. Just by looking at it, you can tell. And how many variables are there? There are three, and each is an integer, so it occupies 32 bits. So you can sort of figure out that these variables will go on the stack. On the other hand, let's try to have, um, let's say an array of size 5. Let's call it X. Yeah. So here's an array of size 5. This will also go on a stack. So now if I run this, the compiler knows that there are these 5 into 4, 20 bytes plus these 3. So 23 bytes. Okay, I'm looking forward to seeing now 23 bytes allocated. So let's just try that. So I've compiled the code and I'm modified the object file. This is the modified file. Let me search for where is that main. Here's the main. Now, okay. So what is now this? It's 30. 30 in hexadecimal. That's 48 plus
Yeah, that's
yes,
48.
48. So 48. So how do we relate it to 48 now? Okay, so this is 5 into 4, 20, and then 12. Okay, there may be some more that it is allocating for something.
I think it's because of the page size. Most probably it's allocating a block based on the minimal possible page size that's going to fit. Again, I'm just guessing.
No, that block is huge compared to this. I mean, this
Yeah,
is
that's
just
4 kilobyte. Yeah.
20 bytes, and this is so that is huge. So that's not it. But sometimes that so this is array, right? So there may be space allocated for indexing this array and so on. Okay, so Yeah, also typically this is to be aligned. Yeah, that's what I think what you meant is that can be aligned and so on. So if you make it a power of 2, maybe we'll be able to see that. So
Yeah.
essentially what I'm saying is this is an interesting thing to play with and to see what the compiler does and observe. Okay, so now it's 8. So
40.
that's 30 plus,
Now it's 64.
now it's 64, right? Okay.
Yeah. Yeah. So most probably, I think some dynamic libraries. But how can dynamic library influence the compiler's code?
Okay, so dynamic allocations are not here. So first of all, here
Yeah.
the compiler knows exactly how much, what are the variables and how much it needs, right? Now, if you want dynamic, or in C, what you do is you use malloc, calloc, and
Yeah.
such things,
Yeah.
right?
Yeah. Yeah.
So that the compiler doesn't know how much. When the program runs, it's able to figure out. Say, for example, you input a number, you ask the user to enter a number, the user enters 10, and then you do allocate 10 bytes. Now here, the compiler will never know what that number is because at the runtime you come to know. So at that time, what happens? How does the program allocate 10 bytes? Now that's very interesting, and that's where we'll see what the operating system does. So essentially, if this is a view of the programmer, right? Programmer thinks that at some 00064A is my instruction, right? And here was that RBP somewhere else, which was pointing to the stack, right? Some base point is pointing to the stack, and stack grows like this. Somewhere else, elsewhere, not where the code is, not where the stack is, but elsewhere, is an area allocated for the heap. So this is kind of used for dynamically allocating spaces. So initially, the process doesn't have it, but if the process wants, it can request the operating system and get chunks of this. So when you actually do a malloc call, you pass the control to the operating system. The operating system gives you this and passes a pointer back to you. So something more complex is happening when you're doing dynamic allocation. Okay. On the other hand, it's very interesting if you don't have these stack variables, but if you have a global variable. If you have a global variable, let's say char c equal to x. This is a here is a global variable now. Or interestingly, if you have a constant, that means this will not be changed. It's a constant, right? Where does this go? This won't go on the stack. This is something which should be visible to all the function calls. If you had instead of a main, okay, you had this function called foo. And then in this function, I was again calling function foo. If the subcondition, if something something, call the function. So this is a recursion, right? So every time you call a foo, the function foo, the stack pointer moves up. So this is the memory. So first time I'm calling foo, I'm reserving some space on the stack and I'm storing my variables. This is 2, this is 3. Within foo now I call the foo again. So stack pointer moves up and it's storing its own copy of the variables 2 and 3 and so on. So for every time the function is called, it should have its separate copy, right? It should not be writing into this because this is a separate function call. That's you want such things like recursion to work. And that's why these variables which are in the local scope, they have to be on the stack. On the other hand, look at this variable. This is a global variable. So this is just in one place and any other functions that are here, they will all see this single variable. So that gets assigned to a different section in memory. So if you have this in memory, somewhere here is your instructions, your machine level instructions. There is an area reserved for all of the constants. Two types of constants, those that are initialized, those that are not initialized. So all of your constants and all of the data, etc., global variables, etc., can be stored here. Then you have the stack for local variables that, so once you exit this function foo, then there's no need of this, right? No need of reserving this space. So at that time, suppose you reserved some space on the stack, you store the value 2, 3. When you return from the function, you just bring the stack pointer back here. So this is as if nobody cares about this now. So stack pointer is here. So stack grows up, you push things on the stack as you call more and more functions. And as you return from the functions, the stack pointer moves down and you push things out. You don't have to erase anything, just by moving the stack pointer, you can sort of create space on the stack as and where required by your function for storing your local variables. Whereas the global variables are somewhere stored here. Say x will be stored here in this area and its address will be known. Suppose its address is 0xf41. So in your assembly program, if you want to read the character x, you will say load a byte from the location 0xf41, for example. So this is very interesting to play with this and figure out where different types of variables get stored. Okay, what if you have a char? What if you have what if you have a string, and so on. Okay. But if you do a calloc or a malloc, remember that the operating system gets involved and things are more complex. So I hope that was interesting. So now let's come back to this programmer's view, right? If you're writing assembly programs, how does this work? Okay. Now, those of you who are not familiar with any kind of a RISC processor architecture, this might help. Such architectures typically have a bunch of registers. Okay. So here are some general purpose registers, and they're numbered from R0, R1 up to R31. So there are 32 general purpose registers. Okay. Some of these registers are special, used for special purposes. Others are just for storing data. For example, in Spark, this register is hard coded to store only 0. Okay, so when you want to, let's say, make something 0, you say move R0 to R1. That moves a 0. So some registers can have special functions in different architectures, but typically there are these general purpose registers and then there are special registers. Okay, so here is a program counter, which is currently keeping track of the memory location which is the instruction being executed. For example, if program counter has this value 004, that means this is the instruction we are currently executing. And next program counter is the next value. Okay, so typically if program counter is 4, the next program counter will be 8 and so on. Why have I said 048? See, because I'm just assuming that this is like 4 bytes long. Each instruction is 4 bytes. Okay. We have seen that in our example, instructions can be of different lengths. That is for the x86. Each instruction can have different length. But in RISC processors, each instruction is of 32 bytes, fixed length. That's nice and elegant because it makes it easy to decode and it makes it easy to even understand this memory map. So PC points to this and next PC always points to the next instruction which will be executed. Okay, so what happens is when I fetch this instruction, I execute it, then I copy the next PC value to PC. So next PC now becomes 8 and the next PC value is again incremented to the next. So it's like initially this is the values, then they move here, then they move here and so on. If we are executing and there are no branches. If there are branches, then next PC value takes up the address. Suppose we want to branch to the location 0x123. So what we do is next PC equal to this. Okay, PC was whatever was, let's say 0x004. We make next PC the address where we want to jump. When we finish executing this jump instruction, what will happen is PC will take the value of next PC. So PC will now become 123 and the next PC will be the one just following that. So this plus 4. Okay, so this is one way of implementing so why are there 2 registers? Why not just have one? So this is a very common feature in many RISC processors where you want to do some sort of a pipelining. Okay, so while you are executing one instruction, you're fetching the next one and so on. So it's useful for that. So we have two program counters. They move kind of in sync, and they move ahead by 4 bytes at a time, unless there is some sort of a branch. Okay. Other than this, we have sort of a register called process state register. In 8085, this may be the flag register. Okay. It has bits, it's a set of bits which store some things about the status of the register, the state of the processor. Let's look at those. Then you have the stack pointer register, the frame pointer register, and so on. We have seen one example of the stack pointer register, right? How it can be used to implement a stack. And then in the CPU, you also have various execution units, the actual hardware that is, say, for doing arithmetic operations and so on. So notice that all of the registers can be inputs to this, as well as all the registers can be input to this. And similarly, the output can be written to any of these registers. So with this, what can you do? You can add R1 to R3 and store the result in R4. Or you can add R1 to R3 and store the result back in R1. Or you can add PC with the number stored in some register and increment program counter and store it back into program counter, right? So you can do all sorts of things. So in the digital design, you have just hardware paths provided from here, all of the registers, and back. And you just control using multiplexers what gets executed. So basically that logic is this. So there is a logic for fetching the instructions pointed by PC, decoding the instruction, okay, deciding what to do with it, activating these execution units, writing the result back into the registers, and so on. So this is essentially what's there in the CPU. And this is what the main memory looks like. It has the instructions. It also has data. It has stack and everything, right? So this is the sort of a low-level programmer's view in little more detail. So this processor state register is very interesting. First of all, it has some flag bits. Flag bits, these store the result of an operation. So for example, if you have an add instruction as here, if this is an instruction to add R1 and R2 and store the result in R3. Okay. If the addition produces a carry, then the carry flag will be set to 1. It's a single bit, it will set to 1. If you have a subtract operation and if you subtract, let's say R1 and R2, but if they were equal, then you get the result to be a 0, right? So the 0 flag will be set in that case, and so on. N stands for negative. So if the result is negative, this will be set, this is a 0, and so on. With this, you can do interesting things, right? See, for example, if you want to do something like in the C code, if A greater than B, then do something, else do something, this is your C code. What we do is we'll put A in some register, let's say R1, put B in some register, let's say R2. Then we do subtraction, R1 minus R2. Okay. If A is greater than B, then 0 flag must not be set, negative flag must not be set. Then R1 is greater than R2, right? So what we have is a conditional branch after that. So what happens is with this instruction, there is a subtract instruction, which will do the subtraction, at the end of which we have these flags set, 0, negative, and so on. And then we can examine these flags and execute the next instruction. So the next instruction could be like, for example, branch if the 0 flag is set to some location. So this is how you would implement, let's say, for example, if A equal to B in C. So if you type out this code in C, run GCC on it and look at the object dump, you might see something like a subtract instruction followed by a branch if equal, something like this. Okay. So these flags are very important and they are set by certain instructions like arithmetic instructions and so on. Then this state register also has some other interesting things. It has things like enable traps and so on. I think at this point, it's It's 11:20. Sorry, I think I went ahead of time. So we, as per the schedule, we take a break and meet at 11:30. But there are any instructions? If there are any questions from you, I could take those up. Yeah. Let me take up the questions and we'll resume exactly at 11:30. So there is a question from Nitesh. He says in this address, okay, this is answered. Adi asks, I could understand where the top 4 instructions came from. Okay, so instructions that were not part of the main. We will discuss that. We will discuss that later. So static variable, where is the static variable stored? That's interesting. So that is also stored in the main memory in one of the sections, the read-only sections. So you have this is a section, typically it's called a text section. It's the name given where you store the code. Then you have .ro data, read-only data, and so on. So you have these sections where these static variables are stored.